Hello, this is homework number 12. We're doing problem number 1. Suppose x of t is a Wieldson stationary process. Show that y of t is also a Wieldson stationary process. So we start this question off by reiterating what we need in order for a function to be a Wieldson stationary process. And we have two conditions that needs to be fulfilled. The first one is that the expected value of y of t must be a constant. The second one is that the autocorrelation of y of t must be a function of a time difference. So here, lowercase Roman numeral number 1, we have the expected value of y of t, which is simply the expected value of x of t convoluted with h of t. And that equals to the expected value of the integral from negative infinity to infinity of x of t minus alpha, h of alpha, d alpha. And further converting that or rearranging the terms, that equals to the integral from negative infinity to infinity of the expected value of the x, expected value of x of t minus alpha times h of alpha d alpha. Furthermore, we simplify the expected value of x of t minus alpha to a constant, eta x, and that further simplifies to the integral from negative infinity to infinity eta x h of alpha d alpha equaling to eta x h of omega. And basically what we need in order for h of omega to be a constant, we need omega to be 0. And so as you can see here, h of omega equals to the integral of h of alpha e to the negative j omega alpha d alpha. So in order for that to be a constant, we need omega to be 0. So we set that to be equal to 0, and that equals to a constant, and therefore the expected value of y of t is equal to a constant. So there is our first so to speak condition to be fulfilled. So our second condition needed to be fulfilled is the autocorrelation of y of t. RY t1 comma t2 equals to expected value of y t1 y t2 y of t2. That further gets translated to expected value of the integral of negative infinity to infinity x of t1 minus alpha h alpha d alpha times the integral from negative infinity to infinity x of t2 minus beta h of beta d beta. Rearranging the terms, we get the expected value of the double integral of from negative infinity to infinity x of t1 minus alpha times x of t2 minus beta times h of alpha times h of beta d alpha d beta. We further simplify this to the double integral from negative infinity to infinity rxx t1 minus alpha comma t2 minus beta h of alpha h of beta d beta. And we know that x of t is Wieldson stationary, and we showed that in Roman numeral 1 the expected value of y of t is also a constant. And so we can further simplify this expression over here. It's basically rewritten to negative. Sorry. We basically, sorry, I rewrote it like a couple of times. Oh, sorry, no. We can basically simplify this to the double integral from negative infinity to infinity rxx of t1 minus alpha minus t2 plus beta h of alpha h of beta d alpha d beta. Further simplifying t1 minus t2 to tau. So t1 minus t2 minus alpha plus beta, h of alpha h of beta d alpha d beta, and that furthermore can get simplified to rxs of tau convoluted with h of negative tau convoluted with h of tau, and therefore you can see that ryt1 comma t2 is a function of tau. And with satisfying Roman numeral 1 and Roman numeral 2, we see that y of t is a Wieldson stationary process. And that is the answer to homework number 12, problem number 1. Thank you.